Recording is on.
Still no icon.
Okay. So let's get going. If everybody can mute their mics, please. Okay, let's get the show on the road. Let's start off with the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. Now that out of the way, welcome to our regular meeting, February 21st. And on the agenda tonight, we have our resident pie guy, Joe B3POR. He's going to be doing a presentation on the pie. And then afterwards, we'll have a group discussion, topic of interest. And the main item will be measurement techniques. And if we have any time left, we can go through any question and answers or inquiries whatsoever. Joe, if you're ready to go.
Absolutely. Okay, guys, I'm just going to go ahead and do the share screen here. All right. Okay. One sec. And can you guys see the presentation? Yes, no?
Yes, sir.
Yeah, okay. So let me start her. Okay, folks, I'm just going to do a quick review of the Raspberry Pi project with a little bit of focus. Like the project has grown from probably when many of you had first seen it. So I'm going to cover a little bit of the form factors as well of what's available now, as well as the GPIO pins that are available in the different form factors. And then after that, I'm going to talk a little bit about the software that's actually available on the Raspberry Pi OS related to amateur radio. And then at the end of it, I'll just show you some quick links that you can go to afterwards. All of it related more for like amateur radio. So the Raspberry Pi Foundation started back in 2008. And actually, back in 2006, there was a response about, it was really a response because there was a concern about the skills of students that were coming in to the computer science program at the University of Cambridge in the UK. So a bunch of guys, Eben Upton, Rob Mullins, Jack Lang, Alan Mycroft, Peter Lomas, and David Braben, most of these people involved with the University of Cambridge, but one or two were more involved with like the open source movement, got together and thought, okay, we need to have a program that, or rather some sort of cheap computer that kids can start playing with early and gain a practical education on computing. And so now the Raspberry Pi Foundation, it's supported both by the University of Cambridge Computer Laboratory and the company Broadcom. And what's also interesting is that the Raspberry Pi Foundation, the commercial arm, is actually looking to even become like an IPO, another becoming a public company and listing on the stock exchange. So that'll be interesting to see what happens with that if they become a public company like that. The hope is that the foundation portion still can continue on doing some of the engineering for boards and form factors that work for hobbyists and folks like us. So we're going to do a quick review of the form factors that are available, and there are actually a number of them now. The first one is this one that you see here. This is probably the one that similar to what you would have first seen. This is the form factor. You've got like the 40 pins. You've got a Ethernet. You've got like 4 USBs, and then you would have audio and video down like this way, and some other connectors. And actually, what you're seeing here is the latest iteration. This is the Raspberry Pi 5. Okay, and so now the latest iteration, you can have choices of 1 gigabit, 2 gigabit, 4 gigabit, or 8. The processor that's on this thing, it's now a quad core. It's a 64-bit ARM processor. It's a quad core Cortex A76, and it's running at 2.4 gigahertz. It also has a PCI interface now, so that'll allow you to put in the what they call the NVMe drives, those type of drives that almost look like memory chips. You also have 2 other of these type of connectors here, which allows you to put higher speed displays and connectors, or cameras and whatnot. Here you've got micro HDMI ports, so you can do 2 monitors, USB power, UART, and also they've got their own. This is called the RP1. So the Raspberry Pi people have already designed some of their own silicon already for input output right here. So they've done quite a bit of engineering, and of course it's wireless. So there's the Broadcom kind of like a little bit of a system on a chip. It's got like the wireless built in as well. Also, the this is the GPIO pins. So there are 40 on board, and you've got quite a bit of selection. So you've got pins that can provide 5 volts and 3.3 volts, outputs that'll give you like a basically 1 or 0, which are 3.3 volts or 0. You also have input pins that can read in 3.3 or 0. You've got some of the pins are programmable for PWM, for pulse width modulation. The pins that are GPIO 10, 12, 13, 18, and 19 are hardware controlled. The other ones are software controlled. Don't ask me what necessarily the differences are between in terms of performance, but there is a difference. 2 of the ports you can do SPI, and there's ports you can do for I2C. There's also serial transmit and receive. That's pins 14 or GPIO 14 and 15. So there's quite a bit here in order to be able to work with. And this form factor, it runs a full Linux operating system. So for those of you who are familiar with Linux, it's running a flavor of Debian. It's based on Debian, compiled to the ARM chip, and you can get 32 or 64-bit available for this. Also, you're not restricted to this Raspberry Pi OS. Some of the other Linux distributions have compiled some variants of their operating system to run on the Raspberry Pi. You can also get Android running on a Raspberry Pi as well, and get access to the Android store and use the Raspberry Pi that way. Okay. Also, when it comes to programming this form factor, when you go onto the Raspberry Pi website and you're checking out how to get started, they tend to gravitate towards using Python. And this is an example of like a simple code to turn on or turn off a pin. And the main library that's used for Raspberry Pi 5 and the current version of Raspbian, it's a library called GPIO 0. And then it's from here you get access to the various commands to deal with the GPIO pins. but you're not restricted really necessarily to Python because this is a Linux operating system. Technically, you can use any language that the Debian distribution that this is based on can use. So you can use C, you can use C++, you can use Java, you can even use Fortran if you wanted to. The only restriction then would be is if that particular language has the library available to support the GPIO pins if you want to use them. Okay. Now, the other form factor that they came out after this main one was the Pi Zero. So again, you've got the 40 pins, and now they've also gone wireless and Bluetooth. And with this particular one, it's a quad, again, the latest ones, which is the Raspberry Pi Zero 2W. That's the current version now. There is a chip called the RP3A0 that it's also a quad core 64-bit. It's a ARM Cortex A53, 1 gigahertz, and you can get 512 megabyte, and the form factor is 65 millimeter by 30. And it's also got 40 pin. It's a 40 pin GPIO, and it's pretty well laid out, very similarly to the main board. It's probably, from the looks of it, it looks almost exact from the previous one. And just like the larger form factor, this uses the Raspberry Pi operating system. So like the big board, this is a full-sized board, or rather a full computer with a full operating system on it. So those two form factors, geared more towards the hobbyists, those effectively give you like a computer with an operating system for you to be able to do whatever you want to do. Okay, so those are the two main form factors that the Raspberry Pi Foundation is using. Now, a new form factor that came out 2 years ago. So now the Raspberry Pi has come out with microcontrollers. So this is an example of Raspberry Pi microcontroller. This is the Raspberry Pi Pico. And they use a chip. Again, they developed it called the RP2040. And this is a dual core ARM Cortex M0 running at 133 megahertz. And it'll have 264 kilobyte SRAM plus another 2 megabyte onboard flash. Okay. And again, here is the pinout. And again, 40 pins. So very similar to the other main boards. But unlike the other form factors, this obviously is not a full-fledged computer system with a full OS on it. This is, after all, a programmable microcontroller. So like the Arduino, you program in C or C++, you write your program, you throw it onto this thing, and it'll just keep running the program continuously. Now, again, when you visit Raspberry Pi and you start doing a bit more digging into the microcontroller, again, they're really big on Python, but you're not restricted to it. When you look at the introduction to programming the Pi Pico, they suggest that you use this open source program called Thonny. So this is a very simple Python environment. And what's interesting is that you can actually, it runs MicroPython. So what you do when you first get one of these Raspberry Pi Picos is that the Pico, you actually drag and drop a Python interpreter of MicroPython onto it. And then what happens is you then connect the Raspberry Pi Pico to your computer running Thonny. You can tell Thonny to then connect to the microcontroller, And then you can actually, when you write your Python program, it actually sends the program automatically down through the USB. It actually executes on the chip, and the SDIO is redirected back to you down here in this little section called the shell. Not only that, if you're using Python, you can even communicate with the microcontroller interactively. So this here, these lines here, down here where the shell is, you can just enter one Python command after another, and you get results right away. It's what they call REPL, right? REPL. So you can actually do a form of interactive programming. So if you're just you're just trying to hack away, you're trying to try something, you want to get an instant result, you can do that. So like on your computer connected through your serial port, like your USB, it's actually communicating through the serial port, running the code on the microcontroller, and you're getting the result back on your computer. And what's interesting is that when you look at, again, the beginner's notes for getting involved, they suggest that you actually use an actual Raspberry Pi, which, like the full-fledged one, which has Thonny already built in and running it. So you can use a Raspberry Pi, 0 or a Raspberry Pi original form factor connected through the USB to the Pi Pico and program it that way. So you almost have like a portable setup and pretty small form factor to boot. But you're not restricted to doing Python. So there's certainly a full implementation of C and C++. And you can also program in ARM assembler. And on top of that, you can also use the Arduino programming environment to program the Pico. So if you go onto YouTube, there are actually some people that show you how to do that, where you pick the device that you're programming, and I think there's some extensions that you've got to add to the Arduino environment so it can detect the Pico, but it's available. You can do that. Now, what you're seeing here, this form factor here, this is actually more geared towards people who are looking at using the Raspberry Pi for industrial purposes. So this one's called the Compute Module 4. So this is actually, I believe, built on a Raspberry Pi 4, or maybe the 3. It uses an ARM Cortex-72, and you can get like 32 variants of this thing. And this is sort of like you basically plug this board into this larger one for the I/O, and again, it's just geared more towards industry. And there's also a connector here for a full-fledged antenna somewhere here as well. So this gears more towards industrial applications, and this also, I think, kind of speaks to maybe why the Raspberry Pi Foundation is looking at getting more involved with commercial, because they've actually got some demand on using these modules for industrial purposes. And here's another example of the Raspberry Pi from an industrial standpoint. Here, you've got the Raspberry Pi Compute Module 3. It's looking very much like a memory module, and it plugs in to one of these boards here, again, 40 pin. So, or actually it might even be looks like it might even be 80 or even more. So again, there are variants of the Raspberry Pi for industrial use. Okay, and as well, if you go onto the Raspberry Pi site, they've got all sorts of things that they've built around the Raspberry Pi. So, for example, the Pi 400, that project, basically it's taking, I believe it looks like it's a Raspberry Pi 4, and then there's a special keyboard with connectors on the inside. So basically what happens is it kind of breaks out the input-output along the back of that keyboard. And so you've essentially, it's a bit like the old Commodore 64, where the whole computer is like packed into a keyboard, and then you just go ahead and connect like a monitor, a mouse, and connect in this way. So that gives you a little compact form or setup. Also, they've got specialized cameras that go into those higher performance MIPI connectors, and they've got two types of them. This version here to the right, this actually allows you to add optics. So if you want actual, glass doing the zoom, you can actually add optics to this particular type. Where this one down over here, this is more for applications like if you're trying to, make a video camera, like a simple one. And there are other makers as well who will make their own versions of cameras going into those ports. And also what you've got is you have what are called the hats. So just like with the Arduino, you've got shields. Here we call them hats. And here's some examples of more towards the amateur radio. So this up here, this is called the Radio Berry 2.0. So this is an SDR hat that you can add. This here to the top right, I believe this is more of a TNC kind of deal that's going on. And then on the bottom right is one of your hotspots, those DVM hotspots. So I personally have two of these guys, and they're based on, I believe, the Raspberry Pi Zero, and they run the Pi-Star software. So it allows you to, you can do DMR, you can do the Yaesu Fusion, you can do D-Star and then it'll connect wirelessly to an internet connection. So then you can hit a reflector anywhere in the internet. And the Pi-Star software that's on these puppies, it'll actually list all the various reflectors that are available. So you can connect that way. And I've over time used these both with the ICOM D-Star as well as the Yaesu Fusion, and actually participated in some of the larger reflectors that are out there. And there's quite a few of them around the world. In terms of the amateur radio software, so because the two form factors that are full-fledged systems, which is the Pi Zero and the main form factor, they've got access to all the various software amateur radio wise that you would typically find on a Linux operating system. So examples of this, here is FL Digi, right? And FL Rig. So all of the FL suite of software, FL Wrap, FL ARQ, that's all available. On top of that, you've got WS JTX, so you can do Whisper, JT65, and the other forms of digital that are part of that, FT8. Down here's an example running. This was on my computer. The grid square. So like as you're making contacts, as you're keeping track of your logs, grid square will actually color in for you like where you've done contacts, and the colors will indicate what kind of contact did you make. Was it voice, was it digital, what kind of digital, and so forth. On top of that, on the bottom right over here, this is geochron. So some of you may know or maybe have seen some of these pretty expensive devices. They were like $500-$600. There are these like dongles that you would plug in, and you would plug it into a large screen, and it would give you a full geochron showing you satellites and where the ISS is, and the day and night line and all the rest of it. And it was pretty expensive. Well, geochron, which is open source and it's on the Raspberry Pi, you can actually just grab a Raspberry Pi, put the geochron on it, even set it up so that when you boot the Raspberry Pi and you keep it on a monitor, you get your geochron. So and here you go. So you don't really have to spend that $500 or $600 with that thing to get all the updates and whatever. You can just do it right off that software right here, and it's very it's very configurable. On top of that, you've got KiCad, you've got fritzing. There's even software to do antenna design and whatnot. I don't recall all the different packages, but there were quite a few. Again, I tried to do this presentation I'm doing with you now on a Linux desktop, so I could have shown you. But the nice thing is, if you have a Raspberry Pi and you put in the graphical interface for the package management, which is called Synaptic, Synaptic actually has categories of software that the Raspberry Pi has access to. And there's a category called amateur radio, and it's quite an extensive listing. So there's quite a bit of software only available that you can get for the Raspberry Pi to work with your stuff. I personally have a Raspberry Pi that I'm using with my ICOM 705. So I've got FL Digi, and I've also got WSJTX working on it, talking with the 705, and it has the cat control and the audio going through the USB ports. In the past, what I've done, for example, the Osmocom, the SDR. So you can actually use a Raspberry Pi if you plug in an SDR dongle. You can get the Raspberry Pi to act like a server for the INQ. So basically, what happens is the software on the Osmocom software will get the INQ from the SDR, and then it'll take that INQ and put it over the network, almost like radio over IP. And then you can get some other SDR software on a different computer that can connect over the network to that Raspberry Pi, and then you get your INQ stream that way. And you can then set up multiple Raspberry Pis with different, SDRs tuned to different parts of the spectrum. So you could actually have, like almost like a multi SDR distributed radio system if you wanted to do it that way. I've also there were some other projects I did in the past where, and this is like on the Raspberry Pi 1 or the 2, where you could have the clock signal show up on one of the pins. And I'm trying to remember the name of the project, but you were able to take an MP3 and then divide up the clock signal and then vary that division based on what was read on the MP3, basically putting out a relatively dirty FM signal. And then you could actually hear, like just, on a FM radio receiver, hear the transmission on one of the pins. So I wouldn't necessarily suggest doing that because you're putting out all sorts of crap and you need filtering and all the rest of it, but it worked. And there were some other projects as well. I dumped 1090. So that was a project that was early on in the Raspberry Pi for picking up the ADS-B transmissions from like aircraft and whatnot. So there's a whole bunch of stuff that's on the Raspberry Pi, either as part of the distributions, or if you dig around a bit more, there's even software that's compilable that can go on the Raspberry Pi for amateur radio. And I promised I was going to keep this relatively short, and we did do a late start, so I'm not going to talk too much more, but give you guys a chance to do questions. But this is the last page of the presentation. What you're seeing here are suggested links if you want to look more into it. So these are all QR codes, so you can take your camera and link to it. There's also the link that I put on the group's IO, so you can actually download this presentation so you can get to this last page and have access to these links. Ones I would suggest, if you're interested in using the Raspberry Pi, particularly with things like APRS, PAT, in order to do the WinLink and whatnot, this channel here, Jason KM4ACK, really good YouTube channel. If you're interested in using the Raspberry Pi controller, the Pico, you can these two down here. The DroneBot Workshop, really, really good. The gentleman who does that is, he's pretty detailed. This one down here, the RPi Pico Ham Transmit. This is a very recent channel, and the gentleman here, he's looking to take a Pi Pico, make it into a transmitter, and then add some electronics afterwards to filter. So he's just getting started. So hopefully this gentleman continues on with the project, because I want to see how far he goes. And the Raspberry Pi Connect Ham software listing. Oh, so that if you go to that link there, it actually lists all, or it's a pretty comprehensive list of all the ham software that you can find on the Raspberry Pi. So it's a pretty good list. Not the full canonical one, but a pretty good one. So that's all I've got for now, folks. I know I really, really zipped through this one. So I'm just going to let people have any questions if they have, to jump right on in.
Okay, I'll get started first. That was a great presentation, Joe. I haven't dabbled with the pies at all, but I didn't know there's so many variants in there. What are the prices like for some of these form factors?
So if I recall correctly, the Raspberry Pi 5, which is the latest and greatest, and if you get it, is it either DigiKey or Newark? I couldn't remember. I think it's around like 100, 145, something like that, like 140, 150, getting around there. If you do the kits, like from CanaKits, where you...
If I could just jump in, 112 for 8 gig Pi 5.
Sorry, how much?
$112 for the 8 gig Pi 5.
Okay. And who was that with?
Most of them, DigiKey, PiShop.ca.
Okay. So just the straight up board, because I remember paying a bit more, getting like with the case, the fan,
right,
introductory book, the power supply, like all the incidentals.
Yeah, I think it's 84 for the 4 gig and 112 for the 8. But
okay.
Everything else is extra.
Right. So then when you get down to the Pi Zero, I think you're getting around 15, 20 bucks, 30 bucks, maybe around that. And when you do the microcontroller, it's about $6, $7. And the slight difference is there if whether or not you've got the pins already in it or not. And it goes even cheaper if you get the variant that's not the W. The RPi Pico W has the Bluetooth and the Wi-Fi. If you just get the straight Pico, I think the cost goes down to like $5 or something like that. Yeah. Okay. Peter, you had a question if you want to jump in? Or sorry, Ken, were you want to wrap up on that?
Yeah. You had mentioned that you can load Android onto it. Why would you want to do that?
Some of the reason why some of the people did that, it was because they wanted to create their own little Android TV boxes. So if you remember those Android TV boxes that allowed you to get all those channels from different countries, you may have seen some of those. So that would be one of the reasons why you would do that. You could actually get a Raspberry Pi, put one of these Android type variants that got you like internet TV, and then that would allow you to do that. I think Kodi was like one of the ones that would do that. And then there were other Android projects like that allowed you to make that little Raspberry Pi like a media center, right? So again, you could actually plug it in to your monitor, and then you could stream stuff to the Raspberry Pi, and then the Raspberry Pi would then put it onto your screen. A bit like the what do you call that, Chromecast? Sort of like acting a bit like that. Yeah.
Okay, that's cool. And all these pies can be programmed through the Arduino environment.
Yeah. So like when you do the Arduino environment, you do Arduino. Arduino has its own what they call SDK, software development kit, right? And that, it could have its own language, like using the Go language. There might be some Java involved. So there's a lot of choice. There's a lot of choice in there. But for our application, I think most people like either using Python, right? Or if there were libraries in C and C++, because that's what you're used to, there would be libraries as well there under the Linux operating system.
Okay, so for a beginner like myself, what would you recommend starting with?
Just to kind of get your head around it, I'd probably follow the advice like from the foundation. Use the Python because that's where most of the support material is. And Python is really not too different. Like when you look at the commands, they're pretty easy to read, not too far off from what you were seeing in the Arduino. And they've got simple examples of turning pins on or off on the GPIO, right? And there's lots of examples on there on how to do that. If you want to get started that way.
Okay, well that was real good. I think Peter had his hand up.
Yes, go ahead, Peter.
Yeah, thanks, Joe. I got a question here. So if I'm in the market for a new computer or laptop, why in the world would I ever buy one?
Sorry, say again.
If I was going to go buy a new computer, say a laptop or a tower or whatever, why would I?
Like it totally it only depends up to you. I mean, like I haven't tried the Raspberry Pi 5 in terms of making it my everyday computer. Like I was trying to connect with the Raspberry Pi 4. It's an 8 gigabit RAM system, and the CPU is no slouch, but I was actually having some issues and it seemed a little slow. So I don't think it has obviously a lot of the graphics acceleration that one would get with a more mainline laptop and whatnot. But at the same time, if you're not doing anything fancy and you're really just needing something to kind of go on to the internet, it could probably just do you, right? For whatever you need. And again, when you go on, if you're looking for something like it's cheap enough that you could even use that system as almost as a way of isolating. Like if I'm doing development work for a little microcontroller, right? I can get the Raspberry Pi 5 or the 3 running Thonny, right? Connect my microcontroller to it. So I've got a very simple, inexpensive, computer system that I can develop on, right? So the only thing I could say is to explore, because everybody's requirements for computing is different, right? So I mean, like for some people, this form factor won't work. No, I don't want to learn Linux. Just get me a Windows machine, right? A lot of people like that. Nothing wrong with with that, because if you're used to working so long with something, go with what you know, right? But what's nice about these little guys is that if you want to explore Linux and you want to use some of the software base to do more work with amateur radio, it's cheap enough to do it, So, yeah.
Okay, thanks, Joe.
Thank you.
Joe, we're getting a lot of echo on this end. Is it possible that it's coming through your shared screen?
I'm wondering if it is. Is it echo, or are you getting like a little, like tap, 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 tap?
No, an echo.
An actual echo. Because I am simply using the...
Stop sharing your screen.
Okay.
Okay, how's that?
Test. Nope, still there.
Still getting an echo.
Must be Eric.
Joe, mute your speaker, mute your
Sure.
mic.
Will do. Hold on.
I've got everything muted, including the recording computer too.
Test. That's interesting.
Went away.
Okay, Eric, start the recording microphone.
Start the record. Okay, it's been muted for quite a while now, but hang on. Okay, it's unmuted.
Test. Is there an echo?
Nope.
Jerry, mute your microphone. Yep, thank you. Okay, so
I'd like to answer Peter's question.
What question's that?
Well, he said, why would I buy a laptop when I could just buy a Pi to do the same thing? Battery management is in the laptop. All your peripherals are integrated. And if you want to carry around one piece, it's all there with the laptop. So if you're going to sit at home, use the parts and pieces of the Raspberry Pi setup.
Yeah. Good point.
especially with the screen and keyboard.
Okay. Yeah, I've always wanted to try a Pi. Never got around to it, but after this presentation, I'm a little more interested now. Go ahead, Frank.
Okay. I just wanted to mention to Joe that I really enjoyed the presentation. It was done excellent. And I'm very familiar with the Pi. In fact, I think I have a version of almost every form factor they put out. And right now I'm using the Raspberry Pi 5 for this meeting. So you covered everything very well. And I learned a lot about some of the programs that are available on it that I didn't realize were there. So you've given me some more things to put on my list of stuff to do. Thanks a lot for the presentation.
Go ahead, Drew.
Yeah, very good. That was an interesting presentation. I'm glad to see other people doing this, and Joe's got it's almost like an industrial focus on it that I didn't know anything about until I recently went to their website and found a whole section for computers only for industry. So that was a surprise to me. A lot more forms than we get here. But I put two links on the chat of software that I use, and they're very handy. The one W3DJS has a lot of amateur radio software built into it as one operating system for the Pi. And I use a 706, very much as Joe described for his 705. And I've been using it for 3 or 4 years now. Works very, very well. The other is Dragon OS, which is, it runs SDRs. And it'll make your SDRs sing. It does all kinds of really quite interesting things. So those two alone, I run Pi 4s, and they are well and easy. They can keep up with all the amateur radio without much problem. Anyways, thanks for that, Joe. It's very interesting.
Okay, anybody else? That's it. Okay, our next item on the agenda is topic of interest, and it's going to be about measurement techniques. And I believe, Peter, you wanted to have this one out?
Okay, well, hopefully everybody had a chance to have a look at the document I uploaded to get the brain cells all going here. So this is really our first topic of interest that we've done, and hopefully everybody will just jump right in whenever you feel like it and offer comments, questions, concerns, whatever. And let's I guess let's see how it goes. So as a reminder, I'll share my window here of the slides. Assume that everybody can see that. So I guess what we'll do then is, well, I'll just start off as was posted. What do we need to measure and why, and what parameters are most important for us? And here's just a list of some ideas, not the end all to be all list, but to get things going. From my perspective, the big one for me is, especially of late, but it flares up all the time, is impedances, especially input, and accuracy that's needed. I'm not sure what everybody else is thinking about what concerns them the most, but I mean, they're all important. And I guess really what you're feeling for now, the project we're working on now is the impedance is a big one, as is gain and losses. For me, it's how to measure this stuff. In the case of impedances, it seems to be much easier to measure them when you're at lower frequencies than in the HF band. So if anybody has any comments on this one, that'd be needed. Oh, and accuracy. I guess with accuracy, how accurate do we need to be? When does good enough become accurate enough? You know, is it 10%, 20%? I don't know. Any comments?
Hey, Peter, are you advancing your slide deck, or are you still on the first slide?
I'm sorry?
I'm only seeing the first slide.
Oh. It should be sharing okay. I got the whole screen up here. What's everybody else see?
Is everyone seeing the second slide?
No,
I'm just seeing the first one.
Just the
The
first one.
title slide.
That's what I'm saying.
You want me to try and show the whole three?
No, Peter, click on the second slide. You're only showing the first slide.
Yeah, I know.
You're showing the title slide.
No, I'm on the first slide. This has happened before to somebody. I don't know why. Here, let me stop sharing. I'll start again. Okay, what am I showing you now?
Yep, working now.
Second slide, yeah.
We can see the second slide and the thumbnails.
Yeah, I'm not going to go to the presentation mode because it looks like something was going on there. It hadn't happened. That hasn't happened to me before, but I know it's happened to others. But I don't remember what cured it. But anyway, any comments so far?
On the question of how much is enough,
Yeah.
I guess it depends on what you're doing. Like if you're measuring impedances, it depends on how much power loss you can tolerate. For small signals, it's not a big deal, but for large signals, it's a lot. Have you guys ever heard of the potato paradox?
No.
Okay, I just read it today. A potato is 99% water. If you remove enough water so it's 98% water, so okay, the potato originally is 1 kilogram, 1 kilo, 99% water. Now you make it 98% water. How much does it weigh?
Okay.
How much water did you remove?
Yeah.
The answer is half a kilo.
Okay.
Because 1 part in 100 was potato, the rest was water, and for it to be 98%, that means 2%, 2 parts. So you need basically, it'll be 1 out of 50 then. That's 2%. So there's a paradox there in terms of accuracy we don't quite always appreciate. So a voltage regulator that's 99% efficient versus one that's 98% efficient, one of them will waste twice as much heat as the other. And so if you're talking about losses in a power amplifier, 99% versus 98% is a huge deal. It's double the heat because the inefficiency goes from 1% to 2%. So whatever it was at 1%, at 2%, it's double that.
Yeah, Hassan, you know what? That's very, very insightful, because what I've found that when I'm measuring things like impedance and low and bandwidth, I'm removing 1% of water. I'm not measuring what's actually there. I'm actually, as your potato example, my probe is removing 1% of that water or 2% of that water. Because I think that's what you're trying to say, right? Is that your device, if it's a certain percent accurate, it's as if you're removing the water from the potato.
That's
Well,
right.
here's another way to look at it on what the accuracy needed is. If you're using components that are, say, are 10% tolerance, then what kind of accuracy do you need on your measurement technique?
Yeah, but I don't think we need to measure that precisely. I don't think it's a matter of, 3.1 versus 3 or versus roughly 3. It's 10 or it's 3 or it's 0. That's the kind of the order of magnitude. Like if it's 3, I'm measuring 3, and I'm supposed to be measuring 3.5. That 3 is fine, or 2.5 is fine. It's good enough for the stuff we do. I think we don't want to get too, I don't know, that's my opinion. We don't want to get too absorbed into the numbers, into
easily done with reading the digital output.
Yeah, no, just we want to get a good order of magnitude to say, yeah, this is around 150, as opposed to saying it's 150.2935.
Another question I'm thinking of, is on measuring impedances. So our bridges are basically set up for measuring 50 ohms. So if I know I have an impedance I want to measure, let's say is 20K, would changing those resistors and whatnot that's in the bridge from 50 up to around 20K be a good idea to do?
The other thing too that that Dave brought up between 3 and 3.5, in your case where you're saying the tolerances, that you might be expecting 3.5, but because of the tolerance of the parts, you may be getting 3. Are you actually going to try and figure out why you're missing half?
I guess it depends if it's Monday or Friday.
Yeah, or if you want to spend your time doing it.
But I think, Ken, what Peter's saying, and it's a different discussion, because I think what the intention here is to look at this list and say, is this what we need to measure? These the things that are appropriate for us to measure. Like, do we care about purity of the signal? Is looking at it on a scope and seeing that it's a clean sine wave, is that good enough? Or do we need to get down, look at harmonics on an SA? Like, how deep do we need to go when we measure this stuff? I think that's what we're trying to get at here, is, how deep. And because the next slide I think Peter has is like talking about how do we measure it, and that's when we'll start talking about bridges and
okay,
that kind of stuff. But here, let's just kind of agree that, yeah, these are the things we need to measure. Is there anything else we need to measure? Is there anything we should strike out from this that we shouldn't need to go and look at?
You said something that struck me there, Dave, when you said, is looking at a sine wave and it looks clean, is that good enough? Or to say, make an assumption that there is no harmonics if it's a nice looking sine wave? Or do you need to check for harmonics? in addition to just looking at the sine wave on your scope.
Well, I personally, if it looks like a near perfect sine wave by looking on the scope, and it's not flat topped at the bottom and top, then there aren't any great harmonics.
But you know, Al Wilkie just posted a video the other day where he's playing with this oscillator and he's just making some small adjustments there. And it's quite interesting to see how minimal of a distortion on the sine wave and the harmonics that it does produce.
And Ken, further to what you're saying, is that up until Peter and I got SAs and whoever else got spectrum analyzers, that was good enough. That's what we used. We used the scope and we looked at it and we said, oh, this looks like a nice sine wave. It's good enough. And so up until, it's like Pandora's box. We opened the box and all of a sudden now it's like, okay, you got to go through and make measurements. So how good is good? What's that saying about good is the enemy of great, or great is the enemy of good? What's that saying?
Good is the enemy.
I have a comment. It's Michael.
Yeah, Michael.
This purity question, superficially, if you're trying to design a transmitter, let's say, and it's got to meet ISCD standards or something, so it's got to be clean. So then you have to look for maybe harmonics, I suppose. I haven't done this, mind you, but you could argue then you have to look at harmonics, and like Dave was doing in one of his other projects. But if it's just an experiment that you're not transmitting something and you're not going to affect anything, then maybe looking at it on a scope is good enough. Or looking at it on an SA if you got one and ignoring the fact that there's sort of harmonics floating around because you don't care. I don't know. That's my thought.
Yeah, and Mike, that's exactly the thing. We've opened up Pandora's box like 10 years ago. When I first joined the group, the group was building, transmitters and receivers, and they would just, throw in a low pass filter and call that a day. Now, I don't know whether the designers actually put it through a spectrum analyzer to check it. I don't know, right? Because I was new to the club. And so there were lots of stuff we were building. And did we actually check it for purity?
Yeah, we did. Simon had the equipment to check it.
Okay, so it comes back to, well, okay, what equipment do you have?
Yeah.
If you've got $100,000 spectrum analyzer, that's a different story. If all you've got is a tiny SA, right?
What might be a good thing to check would be to check the FFT function on the scope and compare that same signal on a spectrum analyzer and just see what the difference is.
Yeah, that's
a really good idea, and I think
because most scopes have FFT functions now, right?
Sorry, what?
A lot of scopes today that you get they already have FFT functions on them.
Yeah, and I guess that maybe my scope does a better job with the FFT function than the tiny SA does, from what little I know about. I haven't used the tiny SA a lot, but it doesn't compare with the spectrum analyzer, for example, because you don't have the resolution. So,
but the assumption there is everyone has got a scope with an FFT, right?
Right. That's
what
right.
happens if you've got an old Tektronix scope, right?
Or if you haven't got a scope at all, and you just you want to use a tiny SA to look at your spectrum, that's good enough, I guess.
I mean,
depending on what you're trying to do.
The scope with an FFT might be good enough, and if you don't want to spend the kid's inheritance like I did and bought an SA, you may find that the scope FFT function is good enough for what we're doing, which comes down to the accuracy, I suppose.
And it all comes down to what equipment you can have. If you can only have a scope and it's an old scope without an FFT, then you have to go with what you see. If you have a tiny SA and you're able to look at it, that's even better. But if you go into an SA and you start seeing all these harmonics, are you going to start digging in deeper now?
Well,
Well,
sure.
then you got to say, are you worried about it or not? Or am I gonna? Yeah, I see these harmonics on the essay, but I don't care. Doesn't
Mhm.
matter to me. I'm just looking for ballpark stuff, right?
Yeah.
I guess.
Yeah, and if you look at, I don't know if you guys have ever heard Farhan talk about how he started. And if you look at how he measured RF, he didn't even have a scope. He
No.
used an RF probe. And he would just use that probe to say, oh, it's oscillating. I've got RF. And that was it.
Yeah. Well,
And his spectrum analyzer was a measurement receiver. Remember, he brought that out to 4 Days of May one time and showed us.
Yeah. And so that's how he built the original BitX.
Yeah. Okay. Maybe we should be, since we're talking about equipment now, maybe we should move on to the next slide.
So I think, Peter, the list is probably reasonable in terms of what we need to measure, right? Purity might be in the hands of the beholder, depending what you have, but certainly, gain, if it's an amplifier, impedances, bandwidth, voltages, frequency, those are fundamental things we need to measure.
And
yeah, and if I'm looking at gain and amplifier, if my measurement says it's, I don't know, 11 dB, do I believe that, or do I think it's maybe 11 plus or minus 1 or 2? You gotta.
Have I got a story for you, Michael? But I'll save it for a different day.
Okay.
Let's go on.
Okay. So let's move on to what test equipment do we need and how do we use them and what are their limitations? So, well, here's our list, and I guess we've all read it and go through it, but does anything stick out in somebody's mind here? Well, actually, scope issues, bandwidth limited here, impedance loading, minimum voltage sensitivity. Well, minimum voltage sensitivity is one thing that drove me to an active probe. Impedance loading, yeah, for sure, same thing. Bandwidth limited. Now, that's an interesting one because, what is the rule of thumb? 3 times the minimum 3 times the frequency of interest you want to go. So 100 megahertz. Actually, Dave, I don't know. We never did make a direct comparison between your scope, which is the same as mine, except yours is 200. And when we start getting up, I don't think there's any difference between a 30 megahertz signal and its voltage level compared to the 200 megahertz scope.
As an experiment, take some kind of oscillator, doesn't matter what it is, and get a resistor that's, say, 10K, and put it in series with that, whatever that oscillator is. You're going to put a 10K resistor. Put channel 1 of your scope probe on that and look at the nice sine wave you get out. Then take probe number 2 and connect it and look at what happens to the probe number 1's waveform.
Right.
You will see it'll drop. It'll drop substantially, especially if you're up around over 20 megahertz, 30 megahertz. That scope probe is loading that circuit.
Oh, I'm sure.
Yeah.
Try it as an experiment. You're going to be floored. And that's what, you see the Dave Jones and the Al Wolke, and that's what they talk about, how the scope probe, it's like a transmission line, and it's got in inductances and capacitance, and it's like a low pass filter.
I guess my thought about, speaking of bandwidth limited, I started out with 100 megahertz scope, I think it was, and then I got a 200, same as you, Dave. But I knew my 100 was 100, so I knew that sort of limited me to what I could accurately measure. So you can do a bit better with a 200 megahertz scope, maybe, but you learn to live with what you got, and that means one way to think of that is, it means you don't go to the higher frequencies. You don't build stuff with higher frequencies if your scope is bandwidth limited.
But it's not the scope bandwidth. This is the probe.
Oh yeah, I know. Yeah, agreed. Yeah, but
Like,
my point.
if your scope, you've only got a 30 megahertz scope, and you're probing 20 megahertz, well, make relative measurements,
Hmm.
right? Because it's going to roll off. But if
Yeah.
you're comparing one signal to another, I think that's reason. And if anyone thinks that's not true, please chime in. I think in that case, you could make relative measurements because all the measurements are going to be attenuated the same amount, right?
That's right. That's right. Yeah.
So I think the scope is okay for making relative measurements, but if you're going to make an absolute measurement, you have to be careful.
Yeah.
But getting back to bandwidth limit, I think 100 megahertz scope is fine up to 30 megahertz.
Yeah. Well, that's right.
I did some measurements with a fluke scope meter I had, and it was rated at 100 megahertz, but it actually didn't have its roll off until it was I think it was about 150 megahertz.
So I've got the function generator that goes up to 30 megahertz only. So that would be okay with a 100 megahertz scope, you'd think, because
Yeah,
you're
but
not.
that's okay if you're got a sine wave and you're looking at a sine wave, it's fine.
Yeah.
Because once you start you're looking at a triangular wave or a square wave, that where you got harmonics.
Yeah. Yeah, that's right. So all depends what you're doing, I guess.
That's where your scope bandwidth comes in. But then, I'm thinking now, okay, well, does it really matter? Because the scope probe is a low pass filter. That's going to filter out all that high frequency stuff. Right?
Yeah. Well,
so then does it really matter to have a 250 megahertz scope versus a 100 megahertz scope versus a 50 megahertz scope?
Well, it depends on whether you're using $10 probes, I guess.
I don't know. I'd love to hear. Is there someone else that could jump in here and comment on scopes?
What about that situation you had with measuring signals?
Well, your voice quality was really bad. Does anybody hear me okay?
Yep, you're fine.
Yeah, Ken, you were really bad there. I didn't really catch what he said.
How about now?
Yeah, that's better.
Okay, I don't know what the heck happened. I had it down, my performance down. I just boosted it up. Yeah, Dave, you had an issue with measuring loads or something last week, didn't you? What happened with that?
Yeah, and that was exactly because of scope. Because that's after I put the scope probe on, I attach a second probe. I was going, wait a second. The signal level is dropping when I attach a second probe. WTF? What's going on here? So after looking at it, I realized that these scope probes, the impedance of these scope probes are kiloohms, not mega ohms. Okay, it's kiloohms at low frequency. If you're dealing with like audio, below a megahertz, yeah, it's probably going to be a mega ohm. But if you get up to like RF to 20 megahertz, it's only kiloohms. And the fact that if you look at Tech's commercial active probe, do you know what they say the input impedance is? It's 40 kiloohms. That's an active probe. Peter, is that right? They said it was 40 kiloohms?
Something like that, yeah.
Yeah. It was like 30 or 40 kiloohms. And they've got it advertised as a 10 mega ohm probe. But they said in the literature it's 40 40 kilohertz, 40K.
So Dave, you're talking about this experiment with the oscillator. What were you doing exactly with the resistor? Putting it as a load to the oscillator?
No. What I was trying to do, okay, so you've got a you've got a amplifier and it's got a very high output impedance. So if you connect your SA to that, you're shorting it out because the SA is 50 ohms.
Yeah.
So your SA is going to read a lot lower voltage, and all of a sudden you're seeing an attenuator. You're not seeing an amplifier, right? So that's when I started to play around to put resistors in series, so I don't load the amplifier down, right? And as I did that, I said, okay, well, I can't use my SA because it's loading it down. Let me just use my scope. So you put your scope on, measure it, and then you put the second probe, and all of a sudden it drops. It's like, hang on a second, what's going on? And there's a really good video. Peter, you watched that video that the guy was talking about DVMs, you know, because like a voltmeter, it's supposed to have a high, I don't know if you call it a shunt resistor across the terminals, the plus and negative. It's supposed to have a high resistance, right? So it's not drawing too much current from your circuit you're measuring, right? And so this guy took a known voltage and he put a whole bunch of resistors, and he went to measure the voltage at each of the resistors, and he found once you get out, I can't remember, once you got out to like 10 or 20K or 50K, the voltmeter was loading the circuit down.
Yeah, I did see that video. I can't remember now. Actually, I can't remember which one it was. But it was interesting because you're right. He went to these different values and it was all loading down on him.
Yeah, Marty put his hand up. Marty, go ahead.
It was a mistake. Sorry.
Okay.
And here I was, Marty would have something insightful and he would let us all know. And all of a sudden, you know, the skies would get clear and we'd hear angels singing and the world would make sense.
Oh, well, yeah.
So let's see, we're getting close to the end here. So just let me pose a question. Let me just jump to the bottom of the list. And of course, if anybody wants to bring up anything on this page right here, just jump in and say your piece. But I did ask the question a little bit earlier, but this is more appropriate here, but the bridges and whatnot. So if you're going to measure something that you know is in, say, just for the sake of the argument, 20K, do you basically redesign your bridge with the 20K values in there instead of the 50 ohm stuff? Does that make sense?
But then your transmission line, your connectors, because those bridges are made with 50 ohm connectors and 50 ohm cables. It's fine to build your bridge with, say, 10K, but all of a sudden now, how you connect to your circuit, that is now you're using 50 ohm cable and 50 ohm terminators.
All right, so then let's if I'm using a 50 ohm bridge and then I got it and I'm plugging in a 20K loaded to there, that's way out there. Is that a valid way to make a measurement, or can I even make a measurement?
I don't know. I would guess that if it's a 50 ohm bridge, then you're talking about what you would put in the fourth leg of the bridge, right?
Yes.
So I guess if it's more or less 50 ohms, whatever more or less is, same order of magnitude, fine. But if you start to, if it's 10 times the magnitude, who knows how accurate it is? I have no idea, but it's sort of.
And that's why I was saying we need to switch to 20. Then as Dave brings up the point, now what about the 50 ohm terminations on the cables and etc.? I heard somebody with their hands up, but I can't see who it is.
That'd be me.
Speak away.
That's Al. Just I recall reading some article there where I guess it comes down to you trying to measure the actual value or reproduce somebody else's circuit. I've seen a few times where they've specified, say, voltages going into a mixer, and they actually specified it was measured with a 50 ohm test instrument, recognizing that the circuit was anything but 50 ohm. So if you're trying to reproduce the original designer's work, you use the 50 ohm equipment, but you probably are not going to get call it a scientifically accurate value. You're just reproducing somebody else's work.
Well, let's go right to what we're doing. Try to measure the impedance of what now?
An iterative process where you start with, say, a 50 ohm bridge, get a value, and then adjust it and continue adjusting your bridge until you finally get it. Hopefully, the editor process would be in the limit converge onto the actual value.
But is the 20-30K too far out for a 50 ohm bridge to resolve it? And even if you did get numbers, how in the world would you calculate it after that? I'm not sure how to do that. Let's say you have an impedance of something that you know is in around the range of, say, 20K or 30K, whatever. How do you measure that, what that impedance is when your bridges are, say, 50 ohms? Do you build a bridge that's closer to the 20K area? But then as they throw in there, you got 50 ohm cables and all that kind of stuff and connectors. Does that have does that do anything to the testing process?
So your 20K impedance is a component or something, and so you build a bridge for that where the resistors are one leg of the bridge is roughly 20K or something, so 40/40, and then you put your unknown resistance there. So there should be no cables involved at that point, right? Like why would you use a 50 ohm bridge for a 20K low impedance? It's just, it'll be so out of range. There'll be very poor results.
But I think Michael here, I think Dave has raised a really interesting point that the connectors that are on the ends of the bridge are most likely 50 ohms. So what do you do then? Just ignore it? Say, well, okay, I know that, but what else, what can I do? Sort of thing. Nothing else you can do.
Okay, guys, let me just show you a little simple experiment you could do. Everyone know what this is, right? This
It's a
is
radio.
an MFJ analyzer. It's
Yeah.
an MFJ antenna analyzer, and if you use it, it'll tell you the impedance of your antenna.
Yeah.
Okay, so take this, turn it on, you'll get an infinite SWR and some wonky resistance, right? It'll be something really, really high. Okay, now take a 50 ohm cable and plug it in, and all of a sudden you stop getting an infinite SWR. It comes down because this is a 50 ohm cable. Well, the capacitor, it's a transmission line, right?
Yeah.
It's unterminated at the end, but all of a sudden the SWR come down. Furthermore, take a terminator. Take a 50 ohm terminator and plug it in. You get an SWR of 1 and 50 ohms because the terminator, sorry, not the terminator, the attenuator. I'm sorry, this is an attenuator. It's a 3 dB attenuator. Okay, so you put your 3 dB attenuator on your bridge, on your MFJ analyzer, and it comes back, it tells you it's an SWR of 1. And it's 50 ohm resistive, okay? And that's from an attenuator. So, Hassan, you're right. And that's what I've been saying all along. And if you read the spec of the MFJ analyzer, it says it can only read antenna impedances up to 600 ohms. If you look at the Nano VNA, the Nano VNA says something similar. It can only measure impedances using 50 ohm system up to about 600 ohms. I see Kevin has got his hand up.
I think Kevin was just saying goodbye.
Here I am thinking again, Kevin's going to say something insightful, and we're going to hear angels singing.
This is the same kind of question, Dave, that when you use a scope and you put a 50 ohm shunt load on it at the scope, at the BNC terminal on the scope, it's the same kind of thing to make it read more accurately. It's the same you get different answers whether you do that or not,
I think it is, but it's different. Here, you're using a sledgehammer to measure a nail. That's might be a bad analogy, but you're using the wrong tool.
Mm-hmm.
You're using the wrong tool to make that measurement. You can't use a bridge when the bridge is calibrated for 50 ohms and all the connectors and cables are using 50 ohms. You can't use that to measure something outside of that 600 ohms.
So if you
And
build
I was blown away.
So if you build a bridge that say is for 20K, and let's assume that
You
the
need
load
to-
that you're testing is 20K, but you're using 50 ohm cables, I wonder how much that would influence it.
Of course it will. It's going to
I know it will. I'm just
influence
saying,
it.
I'm wondering how much.
Yeah, and that's what I'm saying, Peter. Try my experiment with an MFJ analyzer. Just take it, turn it on with an open, and look at the SWR and impedance, and then connect a 50 ohm cable and see what happens
You'll get
to the
one.
result.
I got to
No,
try
you
that.
don't get one.
I got to try that
No,
with the
you
Nano.
don't get one. You don't get one,
What'd you get?
right? You don't get one, or you don't get an infinite because it comes down. Because all of a sudden it's seeing 50-ish ohms or whatever, but it's seeing some kind of termination. That cable is offering some kind of termination to it. I don't know how much termination, but it's offering some kind of termination. In the case if you're building a 10K or a 20K bridge, I think you're going to need 10K or 20K transmission line to go and measure it.
Yes, that's right. Technically, you should never connect anything but a 50 ohm load to a 50 ohm cable. If you connect an arbitrary impedance to a 50 ohm cable, you use a Smith chart to figure out what impedance you're going to see at the other end of the cable, and it depends on the length of the cable.
Well, here's another issue. I thought I'll get smart, and Howard lent me his DNA, and guess what happened? The DNA will only read basically in the hundreds of ohms. I think it actually went up to about 1.5K, and it would see that, but after that, it doesn't see any load past about 1.5K.
Yeah, Hassan, carry on. I want to hear what you were getting at with the Smith chart.
Right. So a transmission line is also a transformer. If the transmission line is lambda over 4, the impedance you see at the source will be the load impedance 1 over the load impedance or something like that. It's like completely the reciprocal. That's why if you look at the manuals for antenna tuners, they will always tell you, do not use this length of coax cable to connect your antenna. And they give you a list of lengths, like 112 feet, 144 feet, whatever. So for for the bands we use, those lengths of lines should not be used because they will cause almost like an infinite impedance at the source. So basically, the only time a coax is predictable and safe is if it's a 50 ohm load at the other end, and then 50 ohms, 50, it's all safe. Any arbitrary impedance, you never connect it with a coax. You connect it directly into the circuit with short leads and all that. So you got to build your own bridge completely, is what I'm trying to say.
And Hassan, I was going to add that. Well, I was going to say that most of the time we're using short lengths of coax. So I don't think it's the length of the coax, but I think it's the nature of the coax because it's got inductance and impedance and all that stuff, and it's representing a 50 ohm transmission line, right?
Yeah, so all the inductance and impedance it has cancels out to 50 ohms. Like that's where the 50 ohms comes from, the inductances and capacitances of the line. So yeah, 50 ohms means all of that.
All right. So then, Hassan, if I heard what you said just a second ago, if I build in a 20K bridge, don't use coaxial cables or connectors to connect it to the circuit. just basically
Right.
jury rig the hookup wire to the circuit.
That's right. Short lengths of hookup wire and short relative to the wavelength you're measuring. So whatever frequency of interest. So that at high RF, like gigahertz, you got to use really short lengths of wire. Basically, you're gonna have to like tiny pins. But at HF, you can use like, I guess, jumper cable, like alligator clips or whatever. It should be fine.
Because I'm seeing basically in the HF range, there's a problem. You can go from like 600K at 1 megahertz down to 20K at 30 megahertz. That big of a drop.
Say again, 600 megahertz, you're seeing what?
At 1 megahertz, the impedance could be indicated at around, say, 600K, 500K, somewhere around there, the impedance. By the time you get to 30 megahertz, it's now down to 20K.
Okay, 2 to 1. That's where would
Maybe
that come
30K.
from?
Anyway.
Hassan, how would you measure impedance? You're an engineer. This is something you deal with. You know,
Yes.
how would you know you've got something with some unknown impedance, and you need to know what that input or output impedance is? How would you go about measuring that?
Oh, you're asking a tough question because every time I would get back into the lab, I would make progress, and then the last thing I do before I gave up is how do I measure impedance peaks, like the resonance peaks. I've never found it. The best way is to use a spectrum analyzer, sweep it. That's the best way. I've always had to do it with a scope and just vary the frequency with a function generator and see where it peaks. But actually, no, that's not what you're asking. You're asking how do you measure impedance?
Yeah, Hassan. One of the things I thought I'd get clever, and what I did was I said, okay, say we're measuring 10K. Let's just say the impedance we suspect it's about 10K. So what you do, you put two 10K resistors in series, okay, connected to your tracking generator and to your SA, and sweep that, and you're going to see some humongous loss. And it should be relatively flat. Now, if you probe the middle between the two 10K resistors and you probe that and it's a 10K impedance, you should see that spectrum analyzer trace drop because you're now you're shorting it out.
So wait, you're
Do you
measuring it?
understand?
No, I don't. Where are the two 10Ks? You're putting them on either
Okay,
side
it's
of
in
them?
series. So yeah, so you've got your tracking generator coming out, and you've got two 10K resistors in series.
Right.
And then you've got your SA, the SA port connected to the other end of that 10K resistors, and the grounds are connected together. Do you understand that?
Yeah, I see that. Yes. And so
Okay,
now
so
you're trying to
now
measure the impedance of what?
so now your sweep is going to show like minus 70 dB or something down because you're introducing those two 10K resistors, right? Okay, so now if you take your device under test and you connect it to the middle of those 10K resistors, okay, so you're going from the middle of the 10K resistors to ground. If it's a 10K input impedance, you're now adding an additional 10K. You're now loading that jig down more, and your trace should drop even more.
Yes, you're shunting current away. That's correct.
Right, right, and so it's going to drop even more. And that way, if it doesn't drop, then you know you may have like really, really high impedance.
So I remember a circuit. Yeah, I remember a circuit in school where they had that type of configuration, and they used 10K resistors to build a 1 mega ohm MP resistor, because when you put that thing in the middle, shunt it to ground, you shunt so much away. I think it ends up being like almost a mega ohm. It might have been in an op amp feedback loop or whatever, but I think
right. But if the idea being if your impedance that you're testing is much, much, much greater than 10K, the spectrum analyzer trace won't drop. But if it's close to 10K, it's going to drop significantly.
Okay, well,
Well, it
maybe.
should drop significantly because you're changing the 10K resistor now in parallel. Now becomes around 5K.
But
Yeah.
if the impedance in the middle to ground or to your device is very, very high, then
The effect is
that's
minimal.
right. It doesn't load the circuit. It's when it loads
Right.
the circuit that you got a problem. So
Right.
if you
Right.
use a 1K resistor to ground, it's obvious that it wouldn't. The SA would be.
It'll be a short
Yeah.
circuit.
It's basically shorting it. That's right.
Now the
But you
problem start getting
you
these
base
results is how do you do the math?
You don't.
I can dig. I can dig up the math for you in one of my textbooks, but in about a week. I'm at the airport right now. But Dave, you just invented the three-legged bridge. I don't know if that's useful, but it's the basically okay. The best, as far as I know, the best way to measure impedance is a bridge, bar none. Bridges are incredibly precise, and they cancel out all the unknown effects. So Lord Kelvin used them way back when, and
No, if it's good enough for him.
yeah. So the only other way to do it is to use a digital signal processor or something. You measure the voltage, measure the current with a current sensing resistor and an op amp, and now you can get impedance measurements through waveforms. And
Well, I'd be interested in the math that you come up with, Hassan. And I know what I've already done this with what Dave had suggested with the two 10K resistors, and that's how I realized originally that there was an issue with the impedance on the probe because the spectrum the curve, the response curve dove, so it came down significantly, and so I knew that this probe is not in the megohms like we all thought it was going to be.
So,
well,
yeah, and Hassan, you don't need any major math to go do this. It's very simple. What you do, you go in LP Spice and you model it. You put your two 10K resistors and you put like a 50 ohm load on the end and a 50 ohm source for the tracking generator, and you feed a signal in, and you get an output, say it's minus 53 dB. Okay, the output. Okay, so now if your SA jig, okay, you run it and you notice that from the baseline to when it's loaded, it drops 4 dB down. So now you go into LT Spice and you say, what resistor do I put in shunt there to bring that down 4 dB? And that there is going to be the approximate value of your resistor, of your input impedance.
Oh, that makes sense.
Where's that
it's
shunt resistor in the middle of the 10K?
Yeah, you attach your device under test in between the two resistors.
Okay, so you just built an attenuator, a pi
That's
10.
right.
Yeah, but if you're what we're saying is if the impedance of your device under test is really high, say a megohm, it's not going to load the circuit down at all, or very minimal. But if
Yeah.
the impedance of that probe is say 10K as well, it's going to severely.
Yes, correct.
Yeah.
Here,
Yeah.
look at my screen. Here, guys, look at my screen. So
Yeah, we
let me
see
just
you.
get rid of all. Let me just get rid of all this stuff here. So, so just,
Well, yeah, there it
and
is.
let me
Right there.
just, yeah. So here's what we build. This part here. So this part here, how do I get this part here? You could see that, right?
Yeah.
That is your tracking generator, or it could be your SNA, the output from the SNA. That's your output. That's your stimulus. Okay? So you have, you have your two 10K. Ignore this. Let me just remove this for the time being. Okay? So now you have two 10K resistors in series, and now this piece here is your spectrum analyzer, or the input port for your SNA. So your SNA or your spectrum analyzer is going to read V out. So you run this and you measure it here, and you will get a reading, say minus 53 dB. So now you know that with your actual spectrum analyzer, you got a 4 or a 10 dB drop. Just with just this jig alone, you sweep it, and now you connect your probe, your device under test here, and the assay drops 10 dB down. So now in LT Spice, you go and you model this, and you get what the baseline value is here without a resistor connected. And now you connect a resistor here, and you sweep through a values of resistances till you get something that's 10 dB lower than what you first measured here. And then this will be the approximate impedance that's connected, that was probed. Does that make sense?
It does. It works, but it's also it's probably not a very precise way. Not the most precise way to do it, I
Yes,
would guess.
for sure. But I think it'll tell you whether it's 10K or 20K or 30K. It's not going to say it's 10.2, or it's not going to say it's 12K or 10K. It's going to say it's of the order of 10K. It's going to be of the order of 20K. It's going to be of the order of 30K.
That's what
But you
you need
just
to know. That's what you need to know. You don't need to know that it's 10.549K or something. 10 is good. 8, 9 to 11 or something, you know.
Yeah. Yeah. See, the other thing that was Dave had pointed out that was starting to really bother me. Then he says, "Well, what are we measuring?" And then the circuits that we're measuring are all low impedances. Anything like 200 ohms, 300 ohms. And I think what you were saying, Dave, I think the highest we've come across recently is the SA612 at 1400 ohms. So if we
And
build a
so
device
most of the stuff,
20 or 30K impedance, it's going to handle that.
yeah, most of the stuff we're measuring is under kilo ohms, and that's why coming back to this and saying, is this much ado about nothing? Are we worried about nothing?
Well, we
You
don't
know,
know.
it's because and Peter, maybe a 20K active probe is good enough.
Well, that's what I'm suspecting, because at the time I didn't realize until you pointed out that the circuits that we're dealing with, the max is 1400 ohms, 1500 ohms. So when you think of it that way, a probe at 20 or 30K, it'll be good enough. It'll be perfect.
Well, let's put it to the group, and let's see, is there any circuits you have built or you've worked with that where the impedance was over 1,000 ohms or over 2,000 ohms?
Well,
Yes, and
you've got one, Dave, with your, could you not do this exact experiment that you showed with the LT Spice simulation? Could you not do it with the SA612, which you know the impedance is around 1500 ohms, and put it in and do this test and see what you get? You know what I mean?
Yeah, exactly. But in that case, instead of using 10K resistors, use 1K resistors.
Yes.
Because
Yeah, okay.
you need
Yeah.
to use resistors that are close to what you're measuring, so you can see the loading factor. Because if you've got you're measuring 1K and you've got 10K resistors, well, then you're basically shorting it out. The spectrum analyzer probably bottom out, right?
Let me ask this question. Let's assume that the device is 10K impedance, and we put it across a 10K resistor like you just described, Dave. How much of a drop do I expect to see on the spectrum analyzer?
Well, Peter, let's go back to my original question. Let's kind of find
I can
out.
actually
Are we?
I can actually answer Peter's question. 400 times attenuation. It's 50 divided by 20,000.
50. Where'd you get 20,000?
10K plus 10K.
Oh, okay.
No, but okay, but are there any circuits, you guys, that we've worked on, any kind of circuits that we've been using that's over 1K impedance? Are there any circuits?
Yeah, your antenna, Dave, your what was it, the random wire antenna? That should be a 3 kilo impedance.
There's always,
With your chicken wire ground.
but there we're using, don't laugh. It's kind of funny. Hassan, every time I transmit, we've got these touch lights in the house where you touch a strip and it comes on. Those lights automatically come on every time I key down.
Oh, that's
Anyway,
a feature, if not.
Do you want me to move on to the
but
last slide, or
in that case, Peter, you got to put a transformer to bring it back down to 50 ohms.
transformer where?
If you've got an antenna that's 6
Oh,
K,
yeah, okay.
6,000 ohms,
Yeah.
you're going to put a transformer to transform that back to close to 50 ohms, right?
I guess you could put variable resistor. I mean, put a variety of resistors with a 10K, and then when you see a minimal deflection, you know your impedance of the probe is up there, up that high point, right? Let me rethink that.
So,
I didn't get an answer to my question, so I'll assume that there are no circuits we deal with that's typically over 1,000 ohms except for an SA612.
To be honest with you, I never really paid attention that closely of the impedances of individual circuits as we were going along until really Phoenix started it. You were going to say something, Hassan?
Yeah, crystal oscillators. So but the problem is their impedance has to be in the, like, I guess, mega ohm region. And so there's no way to build an active probe. I mean, there's no way to build any probe for those. You basically have to build circuitry itself. So I don't think we'll ever be able to put a probe on a crystal oscillator without perturbing it massively.
That's guaranteed.
Yeah.
It's the same thing on the SA612 when you go to hook up your probe on pin 6 or 7 to measure the oscillator frequency. As soon as you put that probe on, it loads it down and changes the frequency.
That's right.
Ken, I was just going to ask that question, that whether if you use a scope probe and you're probing a crystal oscillator, does it change the characteristics of that crystal oscillator? And you just answered the question.
It absolutely does.
But that's because of the capacitance of the probe, not so much the resistance portion of it, right?
Actually, both parts act on it.
Well, I would say the capacitance would be a lot bigger effect on it.
Yeah, mostly.
No, but it's also the Q too, Peter, because all of a sudden that crystal oscillator may need, I'm making up a number, 200 ohms, right? To have it a high Q. Yeah. All of a sudden now you bring in 10K, all of a sudden you're now going to have a low Q, right?
Yeah, no, the crystal oscillator is a good example that you'll never be able to probe it.
And it's also like that. Remember back a month ago, I posted something about measuring the output of a 50 ohm filter, but the 612 has a 1300 ohm input, and the SNA is 50 ohm input. So what I ended up doing is I put I don't know what it was, 1250 and a 50 ohm resistor in series, and I hooked up the SNA to the top of the 50 ohm. Now my question was, I knew the signal would be attenuated because of that mismatch, but would adding that additional resistor of 1250, would it change the bandwidth of the filter? Because now that resistor is acting on the Q.
Yeah.
But it's a small, if it's the way I think about this, Ken, if that 50 ohms is small compared to the other resistor you put in series, then it's not going to impact it much. Like if it was, let's just say, I'm going to give an extreme example. Let's just say it's 1 meg. You had a 1 meg resistor, and then you're putting 50 ohms. Well, that 50 ohms compared to 1 meg is tiny, so it's not going to make a difference. If it's like 100 ohms, and then you put 50 ohms, then yes, it could, because you're now introducing 150 ohms. But if you've got 1K and then 50 ohms, that's 1K, 1050 ohms. Is that going to impact the filter much? Maybe not. I don't think it's going to impact it very much. Would it? I don't know.
You'd have to LC spice it to start off to get an idea.
An experiment. And the other issue too is, remember we're feeding the SMA, or SMA, no, the SIGGEN into the pin 6 of the 612. Well, we're running 50 ohm SIGGEN, but we didn't know what the impedance on pin 6 was. And when I was experimenting with the attenuators, I was having a heck of a time getting a matching peak-to-peak voltage like you guys were. And as it turns out, that my attenuator output wasn't 50 ohms. And as soon as I put that 50 ohms in, then our signals matched. And because, as I found out later on, reading somewhere, that's pin 6 input has a very high input impedance. So if we're using 50 ohms signal, it doesn't matter.
Ken, I think you're hitting the nail on the head here, is that I think we have to be clever in terms of how we measure things. And we may not be able to use the tools at hand, and this is why, because I'm always doing little experiments. I'm doing little experiments to see what happens. What do I get? The other thing that happens with that jig, everyone thinks, oh, that's a clever jig. The problem is that those 10K resistors, they have inductances and impedance and capacitance. So when you trace it, you don't get a flat line. You get a curve.
It's a good point. So I started off, I put mine floating in between two connectors on a PCB. I ended up taking it all off and just had the two resistors floating in free air because of the capacitance of that jig was so high. But we've done that.
And so, so you're always.
What was that?
Where's my? Hang on, I got to find my little jig here I made. So Peter, this is where I got clever. I don't know if you could see this.
Yeah, it's
see this? It's got two SMA connectors, and it's got a 10K resistor in the middle, two 10K resistors, and so in the middle is where I would put my test. And even this, I would sweep this without anything connected, and I would not get a straight line. So just from this, you're picking up stray inductance and capacitance, just from that. So it's like, and so this is how I spend my time, is like just struggling and scratching my head and trying to figure this crap out. But Peter, I think we should call this a night. It's like 9:30.
Yeah.
So and I think this is a good discussion. Maybe we should have part 2.
Yeah, the part 2 would be the I guess the test gear that we could build at home, that kind of thing. So we can cover that off on the next meeting, I think.
Yeah, and I think people can. I think everyone can now appreciate the issues and maybe go away, think about it, because the whole thing is we're trying to figure out what are some clever ways that we could measure some of these things. Is there a simple, clever way that we could measure it where we don't have to go and buy, a $500,000 piece of equipment?
So Dave, before on that note, Dave, you're talking about measuring impedances, right?
Yeah.
Yes.
Yeah. I was obsessed with this. And bandwidth. I was obsessed with this a while ago, and I found this one paper from like 1950 with one description of a device, basically a donut, like an annulus. kind of like two concentric rings made of carbon or something. You apply RF to the outside, and it's basically a resistor which has no frequency dependent effects. So that's, and they were using it for ratiometric, some kind of measurements for a bridge or something. But
Does that mean, Hassan, does that mean if we, because these resistors are all metal film, so if we were to go back to old school carbon resistors, we would get better frequency response?
possibly, but if you make it into a ring shape, so okay, so I think carbon resistors are always known for having better RF properties, but it's still a straight line. If you make it into an annulus, I think all the magnetic fields cancel out because the current's going in from all directions. So there's no magnetic field, therefore zero inductance. So that
I see what you're saying. Yeah, I see, because that cancels it out. Yeah, and since there's no parallel components, there's no capacitance as well, right?
Exactly.
Yeah.
So when you get back from the Caribbean, we'll come back to that again, Hassan.
Well, I'm gonna have to. It took me forever to find it on Google, and if I tried, I would never find it again. It was so obscure. So I'm gonna have to dig up my old hard drive to see if I still have a copy of this thing, because
But you know
it
what?
was.
There's got to be a clever way of doing this. There's got to be a way. Other people have done this. Like, you know what? It'd be really interesting to have a conversation with like someone like a Wes Hayward. And because I'm sure he's run across and some of these, the movers and shakers in the RF world, in the radio world. I'm sure they've run across this, and
Well,
they've had to.
there is a chip from Analog Devices that does an like 1,000 FFTs a second or something, or I don't know, a really big FFT, and it can do like 24-bit impedance measurements. The only problem is it's only up to 10 kilohertz. But they use but they basically just digitize the signal, do the FFT on the current waveform and the voltage waveform, see how much they're out of phase, and so 24 bits of resolution, like ridiculous levels. 24 bits. That's like 16 million to 1 range. So, but it's only up to 10 kilohertz. So you could build something like that for RF, HF, but it would be like really cutting edge stuff.
Well, I was looking at
you know what?
You look
know what,
at
Hassan?
Go ahead, Dave.
No, I was going to say, Hassan, you look at like high-speed digital logic. You're talking in like, you're talking like gigahertz clocks and stuff like that. Probably those people who are measuring that, they're probably not using scopes. They're probably using one of those digital analyzers. I guess they've got some kind of front end to measure the square wave. It's just like a Schmidt trigger or something. I don't know.
Oh yeah.
Because they wouldn't be using scopes, because that would really load down the signal trace, right?
True. Although from what I've heard, 20 kilo ohms for an active probe is really good. Like, I saw a book from 30 years ago, and they were saying that 3 kilo ohms is actually pretty good. And you just live with it. You just make sure that, like, most RF circuits don't have high impedances anyways. Like, all the impedances are really low. So
that's what I'm kind of surmising, Hassan, that most of the circuits we deal with, like a 20K probe impedance, is good enough.
Right. The only question is it constant across the entire frequency band? So all the harmonics are attended equally?
No, it's not. No, it's not, because if you look at an active probe, if you look at a Tektronix active probe, or even your scope probe, you measure a audio amplifier, it's 1 meg. The impedance that it's introducing to that circuit, it's probably hundreds of kilo ohms, if not a mega ohm. So that's why your scope, it says, oh, it's 1 mega ohm, but it's 5 picofarads. So they're saying, oh, it's this, but it's got 5 picofarads. So that 5 picofarads at RF is now shorting your your circuit out, right? That's why now I look at all my equipment, it's got a capacitance. And the Tech Active Probe says it's 40K at this frequency, but it's got 5 picofarads, or it's got 1 picofarad.
I see. So basically, a 10x probe also has capacitance, but they let you tune it out. So it's basically a fixed capacitance. So what you see
Yeah.
is the capacitance is constant across all frequencies, but it does mean there's a frequency dependent attenuation, a first order capacitive roll off. So that's the best we can hope to achieve, which means the higher you go in frequency, the worse it is.
Right, and that's why the probe goes down to like 8K at like 20 megahertz,
And
or like 30 megahertz. It's down to like 8K. So all of a sudden, you go and you probe a 1500 ohm circuit with 8K, you're going to take it down.
but you get into 150 megahertz, and on our circuit here, and your probe is starting to show like 2K. So,
Yes.
so I mean,
lower.
how these probes get rated up at gigahertz, I have no idea. I mean, does gigahertz circuits
Yeah.
only deal with 50 ohms or 10 ohms or something? I don't
That's a
know.
good
Yeah.
question. Yeah, how do they do that? How
Anyway,
does the gigahertz probe work?
anyway, guys, I think it's everyone's dropping off. We've gone way over time here, so I think we should, Peter. I think it was a success. I think we should table this at a subsequent meeting where we could continue this discussion. I think there's a lot of people, or maybe we can do a poll on the group and just ask everyone: was this interesting? Should we do more stuff like this?
Mm-hmm. Well, I think so, as long as we have the right topics, of course. Now, the remaining topic on this particular topic is homebrew gear, or what can we build to help measure what we're talking about. So we can cover that off on that particular slide off of the next meeting.
I would the next conversation start off with that second slide and say, this is kind of where we left off.
Okay.
These are the issues. This is what we found. So now let's carry forward.
Okay.
But anyway, let's kind of, because I think it'll be good. Everyone knows the issues now. They understand. Maybe some people go away, think about it, and come back and with some clever conceptual things we could do, right?
Yep. Good idea.
Okay, guys. So
Take care.